All right, now as I go through this, you're not going to need to write everything down like word for word that you see up here, because you do have a lot of it on the sheet, the booklet that I gave you yesterday for review. So you might want to have that out so you kind of know what things I'm doubling up on and things that you don't necessarily need to write down. Okay? All right. First thing we went over in this unit, okay, was the types and forms of energy. And we talked about chemical energy and nuclear energy and electrical energy and some of the people who were involved. Okay? So yeah, that's certainly going to be on there, okay? It's going to be multiple choice stuff, right? I might, give you an example of, some kind of situation involving energy and ask you what the main form of energy would be, okay, in that thing or something like that, okay? Or I might ask you things like, a ball rolling down a hill has which of the following kinds of energy? A, chemical, B, nuclear, C, mechanical, D, potential, okay? And you'd have to pick your best answer. Incidentally, on that example, 2 of the answers would technically have been correct. Which one would be better, mechanical or potential? No, mechanical. If it's rolling down a hill, it has potential, but it also has kinetic. Therefore, mechanical would have been the best answer, okay? And it is always about picking the best answer. Lots of times there's more than one that's right, okay? But every time there's one that's better. Okay, everyone follow me there? So you want to read a question like that kind of thoroughly. Okay, that day we also talked about systems, open, closed, and isolated. Okay, just terms that you'll need to remember in case they come up in a question. Okay, an open system exchanges matter and energy with the surroundings. Closed system exchanges energy only, and isolated exchanges neither. Okay, once we had talked about systems, then we went on and talked about thermodynamics. We talked about perpetual motion machines, heat engines, and heat pumps. Okay, so we talked about the laws of thermodynamics. The first law of thermodynamics was the law of conservation of energy. Okay, energy of a system stays the same unless work is done on the system or the system does work. Okay, but then the second law of thermodynamics, what was the second law of thermodynamics? Heat flows from hot to cold. Okay, and that was the basis for talking about heat engines and heat pumps. Okay, heat engines use the second law of thermodynamics. Okay, as long as heat is flowing from hot to cold and we put something in the middle that can capture that movement, okay, then we have a heat engine. Right? And we said that like a jet engine was an example of a heat engine. And then we talked about heat pumps like your refrigerator and how they use energy, kind of like active transport, to move energy the other way, up the gradient. Okay, that is that they pump the heat from a cold area into a warm area. All right, so from the inside of your fridge to the surroundings. Okay, or an air conditioner from the inside of your house to the hot outside of the house. Okay, things like that. Is that ringing a bell? Okay, so just review that because there's probably some multiple choice questions about that. It is possible that you could have a question involving explaining why or why not a perpetual motion machine could exist. Okay, and I would say that anything involving that would need explanations to do with thermodynamics. Okay, then we went over these. Okay, scalars and vectors. Okay, it is important that we remember what things are scalar and what things are vector, because if you're asked to solve for them, you need to solve for them the right way. Okay, the places where that's kind of most important would be if a question tells you somebody went 20 meters north and then 5 meters south, calculate their speed. Then north and south didn't matter. Okay, you got to remember that speed is scalar and direction doesn't matter for it. Okay, or that distance is scalar and the direction doesn't matter. Okay, things like that. So that's why you have to know which ones are scalar and which ones are vector. Okay. Right. It's also important because if I ask you calculate the acceleration in this problem, that your acceleration needs to have well, yeah, meters per second squared is the units, but it also has to have direction because acceleration is a vector quantity. Okay, things like that, just little things that sometimes will nickel and dime people of marks, okay, on a test. You know, they'll just forget, they'll do the whole question right and forget that acceleration is a vector quantity and lose mark. Okay, so little things like that. We don't want to lose marks needlessly on something. All right, so while we were talking about that, that was the first day we talked about V equals D over T. Okay, certainly there'll be some V equals D over T stuff on the test, but it's not something that's in like really time consuming, so expect that you probably have that on the multiple choice, maybe as part of a graphing question, okay, because there's also going to be some graphing in there, so it's possible you might need it for that. Okay, graphing. How important is graphing? Huge. Most important tool in science is graphs. Okay, so we've got to know how to read them, interpret them, calculate things from them. How many types of graphs did we do specifically? 2. Position versus time, velocity versus time. Okay, expect that there are going to be many graphs on the exam. Okay, so you're going to need to be able to calculate things from those graphs. So remembering that from a position versus time graph, okay, that we can calculate. So here's our position versus time graph, right? The slope of the line is going to represent what? Speed or velocity, okay, especially if it's vector, right? Okay, so if I've got a position versus time graph here, okay, then, you know, if I calculate the slope, essentially I'm dividing displacement by time. Agreed? Okay, so things like that to remember. Okay, being able to use this, okay, got to be able to use that. I'll tell you right now, in the written response, there's a graphing question. I built a graph on Google Sheets. I had it spit out the equation. It's on the sheet. It's on the test. Okay, it's instead of on the right-hand side, though, I put it inside because then it was all there instead of on 2 lines. Okay, and then I'm going to ask you, use it to calculate the following things. All right, so you've got to be able to go, okay, what does every part of y equals mx plus b represent? Y is a y value, x is an x value, m is the slope, b is the y-intercept, okay? Be able to use those and calculate things from graphs. Okay, for a velocity versus time graph, okay, sorry, on the position versus time graph, if I'm asked to calculate displacement, final position minus initial position would give me the displacement. If my graph isn't just one line, if it's a whole bunch of little squiggly things, okay, maybe it goes kind of like this and then back up there, right? How do I calculate the total distance? Yeah, add all the sections together, right? Distance is scalar. It doesn't matter whether it went up or down. Okay, if it's displacement, then it's final position minus initial position. Okay, things like that, things that we'll need to go over. There are some graphs, obviously, on your review package, okay, that you can use kind of to practice and review that. Okay, from the velocity versus time graphs, if I calculate the slope of this line, what is it going to represent? Acceleration. Okay, I know it's acceleration because I'm going to be calculating a change in speed divided by a change in time. Okay, so it's going to represent acceleration, right? And if I calculate the area underneath that line, what's it going to represent? The displacement. Okay, we did that on the Need for Speed Lab. Are you going to be asked to do that on the test? I 100% guarantee it. Okay, so you need to know how to get everything we ever talked about from the 2 kinds of graphs we talked about. You got to be able to do it. I'm going to ask for all of it. Okay, graphing on this test is probably 15%. Okay, that's just a rough estimate. It's maybe more, but it's for sure 15% of the test. Okay, so it's a good chunk. All right. After graphing, we talked about acceleration because we did the velocity versus time graphs, and then it was kind of a natural transition to what acceleration is. Okay, so acceleration is a change in velocity over a time interval. Okay, that formula. Will you have a problem on the written response that asks you to solve a acceleration problem? Probably, like, definitely. Okay, going to ask you an acceleration problem where you'll have to manipulate that. I probably wouldn't give you one on the test that said, here's final, here's initial, here's time, calculate acceleration. There might be one in the multiple choice, but in the written, you definitely have to do some manipulating. Okay, most important concept, work energy theorem. There's some multiple choice questions about work energy theorem, but they're situational. Okay, they're more of understanding kind of questions. Kind of like, how many times did we go over the bow and arrow? Okay, if I do work, what does that work become? It's kind of those kind of questions. There'll be some of that in the multiple choice to see if you understand work energy theorem. But the problems are in the written response. There are 2 of them, and they are 6 marks each. They account for close to 20% of the marks. Okay. So should you know how to do a work energy theorem question? If you think not, this is not the class for you. Okay? Okay? You definitely need to know how to do that. Do you have lots of examples with the answers already? Yes, you do. Can you watch podcasts where I solve a whole bunch of them? Okay. Advisable to do that. Okay? If you're struggling. If you know how to do them, good. Then you're set. All right, so work is force times distance, which is a change in energy. Okay, that could mean change in kinetic energy, change in potential energy. All right, like I said, we've gone over example level questions a bunch of times. All right, and then the last thing, conservation. Oh, sorry, second last thing, conservation of energy. EI equals EF. Okay, figure out, do you have potential and kinetic on both sides, or any of them 0? What can you do with the mass usually? You can usually cancel it. As long as you're not being asked to calculate one of the types of energy, you can cancel mass. Okay. Okay, and then the last thing, which we're going to talk about on Monday, okay, only take about half the class on Monday, it's a pretty easy concept, is efficiency. Okay. And efficiency just has to do with how much of the work you put in actually does useful work. It's just a percentage. Okay, so if I put in 100 joules of energy into a system and it only does 50 joules worth of work, it's only running at 50% efficiency. Okay, it's an easy concept. Okay. Okay, so that's work out divided by work in. That's what the formula is, but we'll talk about that on Monday. Okay, so this is the useful work output that the system does, always the smaller of the 2 numbers, and this is the work that you had to put in, or the energy that you put in. Okay, it's just like what you get on it if you want to calculate your percentage on the test. It's always what you got divided by what the test was out of. That's either equal to or smaller than this number down here. Okay, so the smaller number is always the one on top, because nothing can work at more than 100% efficiency, can it? Because if it does, what is it doing? It's creating energy. So if you get an answer when you do an efficiency problem that is 120%, you have definitely done something wrong, or you've discovered the greatest thing ever. But you probably did something wrong. Okay. All right. Questions on that? That's all there is. Okay, but expect that a pretty good chunk of this is graphing. Good chunk of it is work energy theorem. All right, give you a few more details here about your test. Okay, so like I said, your formula sheet is on the test, so you can't use yours, okay? But it's exactly the same thing as what you have, except instead of being 1 column, it's 2, okay? There are 20 multiple choice questions, and there's 45 marks in the written response. Okay, 45 in the written, not 45 questions, 45 marks in the written response. Okay, so multiple choice, like we said, there's some stuff about your understanding of work, there's some stuff about the different kinds of energy, some stuff about thermodynamics, systems, okay, some stuff about understanding vectors and scalars, okay. There's some very minor, very easy calculations in the multiple choice, like using formulas without having to manipulate them, or using really easy formulas like V equals D over T. Okay, that kind of stuff would be in the multiple choice. There's one graph in the multiple choice. Yeah, you know what? The bulk of the multiple choice is understanding of scalars and vectors and energy. Okay, that's the bulk of it. Okay, written response. Okay, graphing, acceleration, graphing, work energy theorem, conservation of energy, acceleration. 7 questions. All right, 45 marks, 7 questions. Now, your graphing questions both have an A, B, and a C part. Okay, that's kind of where the marks kind of start doubling up there. All right. Give you a pretty good idea of what to expect for Wednesday, or for those of you that are doing it on Tuesday. Okay. Although for those of you doing it Tuesday, your test is a little different. So you got another 20 minutes, 15, 20 minutes here of class. If you want to work on that review sheet, or if there are any questions, I'd be happy to answer those. Yes, the review sheets I actually put in the 4th drawer already. Okay, so there's a worksheet from yesterday and a question and the review booklet in the 4th drawer.